Hello, our project is a review of PAPR reduction schemes in coded OFDM systems and simulating a subcarrier phase control based PAPR reduction scheme. First, we're going to discuss OFDM systems advantages and disadvantages, and then we have a review of PAPR reduction schemes. And then after that, we're going to describe our proposed method for PAPR reduction in OFDM systems, and finally we will illustrate our simulation results. Multi-carrier transmission such as orthogonal frequency division multiplexing is a promising technique to realize high bit rate wireless transmission systems, where parallel data streams are transmitted with multiple narrowband subcarriers and those inter-symbol interference is mitigated. OFDM systems has several advantages. High bit rate, efficient use of spectrum, elimination of ISI and IFI, simpler channel equalization, co-channel interference, and impulsive noise protection. It also have some disadvantages. Uh, the OFDM signal has noise-like amplitude with a very large dynamic range. Therefore, it requires RF power amplifiers with a high peak-to-average power ratio. Also, it is more sensitive to carrier frequency offset and drift than single carrier systems are. A major drawback in OFDM system is that the transmit signal exhibits a high peak-to-average power ratio, which causes nonlinear distortion and spectrum spreading at the output of power amplifier. As a solution to the PAPR problem in OFDM systems, several techniques have been proposed, such as deliberate clipping, subcarrier phase control-based methods, and coding. The deliberate clipping is a simple technique, however it causes out-of-band radiation and in-band distortion. Although filtering after clipping can eliminate the out-of-band radiation, it may cause considerable increase in the peak power. As a subcarrier phase control based method, selected mapping and partial transmit sequence techniques have been proposed. SLM and PTS are the peak power reduction technique which reduces the probability that high peak power occurs. In PTS, PAPR of OFDM signal is reduced by grouping all subcarriers into several clusters and adjusting the phase of each cluster by multiplying weighting factors so as to minimize the PAPR, symbol by symbol. In SLM, random phase sequence is multiplied with transmit sequence and the sequence which minimizes PAPR of OFDM signal is selected from all possible sequences. However, this method causes transmission deficiency because redundant site information on phase rotation value or selected sequence has to be transmitted to the receiver. In addition, if the transmission error occurs in site information channel, it would result in the demodulation failure. The coding technique is capable of PAPR reduction and error correction. The basic idea of this coding technique is to avoid the use of code word with high peak power. Although the redundancy of this code word is used for error correction, it is necessary to find a specific coding algorithm to search a suitable set of the code word with both low peak power and high error correcting capability. In our project, a subcarrier phase control based PAPR reduction method without site information transmission is used for LDPC coded OFDM systems, where the phase sequence is multiplied at the transmitter to reduce PAPR. On the receiver side, the phase sequence used for PAPR reduction is estimated without site information by comparing the decoding results regarding a limited number of candidate phase sequences. For example, based on reliability information of each received bit, a limited number of candidate phase sequences are selected from all possible phase sequence patterns. and likelihood values corresponding to these candidate sequences are calculated to estimate the selected phase sequence. Figure 1 shows system configuration of LDPC-coded OFDM system with the proposed method. The code word vector is mapped onto complex QAM signal. The transmitted data sequence is multiplied by a random sequence that is selected to minimize the PAPR of OFDM signal. The SLM-based system is considered as an equivalent PTS system. The computational complexity, for example, the repeated IFFT operations to find the sequence which minimizes PAPR in SLM system is reduced by PTS type configuration. In PTS-based system, the data stream is grouped into several clusters. Each cluster signal is individually modulated with inverse fast Fourier transform to generate output signal of each cluster. The IFFT outputs of the second to the last cluster are weighted by phase weighting factors BIs. The best combination of weighting factors is selected so as to minimize the PAPR of the signal after combining all cluster signal symbol by symbol. In SLM-based PAPR reduction method, the best sequence which minimizes PAPR of OFDM signal is selected from a set of random sequences. The random sequence is generated by linear combination of basis vectors constructed based on parity check matrix in LDPC code. Figure 2a shows examples of basis vectors, and the corresponding parity check vectors are shown in figure 2b. Each binary sequence is generated by linear combination of basis vectors. For example, a random sequence is given as the summation of multiplication of i's and ci's, where a1 is a 0 and ai's can be 1 and 0 since we are using a Galileo's field of 2. The best sequence which minimizes PAPR is selected from all possible candidate sequences. Basis vectors in figure 2 are constructed based on Gallagher parity check matrix. To decode the received data, we need to estimate whether weight factor is 0 or 1. In the proposed method, weight factors are estimated as some product decoder which offers not only error correction capability but also weight factor estimation. To explain basic idea of weight factor estimation in LDPC coded system, a simple example of weight factor estimation is shown in figure 3, where the transmit QAM symbols corresponding to one's position in the selected sequence is multiplied by -1. From the principle of parity check vector, if no transmission error occurs, it is obvious that unflipped bit is detectable as error. Figure 4 shows an example of Tanner graph expression to explain extrinsic value calculation process, where color circles in symbol node stand for symbols corresponding to one's position in J's parity check vector. Red and green color circles correspond to flip symbols and unflip symbols respectively. From the property of the sum product decoding for LDPC code, we can expect that the extrinsic outputs are correctly determined only when the phase sequence is correctly estimated and removed from the received sequence. Because the reliability information on channel condition does not match the received bit error attributable to bit flipping occurrence in the SLM method. This idea suggests that the extrinsic outputs would take the highest value when the phase sequence is correctly removed. So it is expected that the correct phase sequence is estimated by comparing the decoding result of the received sequences multiplied by each candidate phase sequence. After extrinsic values are obtained with single iteration sum product decoding for possible candidate sequences, average absolute value of these extrinsic outputs are calculated. The SLM sequence with the highest average value of the extrinsic output is selected as the correct phase sequence. Performance of the proposed method is evaluated by computer simulations. Table 1 shows simulation parameters. We consider an LDPC-coded OFDM system with NC subcarriers. LDPC code-off rate half is employed with sum product decoding. To clarify the effect of peak reduction, CCDF is defined as a complementary function of cumulative distribution function. CCDFs of instantaneous power of OFDM signal normalized by average power are shown in figure 5, where QPSK is used as subcarrier modulation and the number of clusters is EEL6, 9, and 11, which corresponds to the number of candidate sequences in S element with 32, 256, and 1024. The figure 5a shows our result in our project, and figure 5b is adapted from the original paper. Figure 6a and b show block error rate BLER performance of QPSK of the OFDM system with perfect estimation and without perfect estimation. From the figures, it is obvious that the correct estimation is important for avoiding error propagation. And figure 6c shows the results from the original paper. In this project, we use a selected mapping method to reduce the PAPR of OFDM system without using side information. On the transmitter side, the PAPR is reduced by multiplication of a phase sequence. At the receiver, the phase sequence used for peak power reduction is estimated without using side information by only comparing the decoding results of a small group of candidate phase sequences. Using this method, the error propagation is prevented. The computer simulation results shows that for LDPC code with code rate of half, a 2.4 decibel reduction in PAPR of OFDM signal is achievable without remarkable BLER degradation. Thank you and goodbye.